Hello and welcome to this software optimization fundamentals video on higher level languages. So last time we discussed a basic FDE cycle in which we produce some binary instructions in memory and these get fed to the processor to execute. And mostly we were talking about this in the context of assembly code. So we can write some textual representations of instructions which can then get translated into the appropriate binary sequences. But although writing programs in assembly code is hugely easier than writing them in machine code, it's still a very tiresome process. Remember, modern processors are very fast, and so writing every single instruction that we might want them to execute can take a while. As a result, we have languages to abstract machine code further, such that more abstract ideas can be written in some textual form and then go through a more complex translation process to machine code to actually execute in a particular processor. We call such languages higher level than assembly, as they're more abstracted from machine code. These languages are typically defined via standards, which define their form and behavior, such that people can write translators for the language which abide to the standard. And this can help avoid inconsistencies between translators. To try and avoid the case where I can write some code and it compiles fine using my translator, but then I try and compile it for your particular architecture using your particular translator and things don't work properly. An example of a language which is defined this way is the C programming language. And this is actually a screenshot of part of the C99 standard here. So this translation process for higher level languages may perform some kinds of arbitrary manipulations on the code, often to optimize for certain properties, for example performance. So one thing that a lot of translators, particularly compilers, do is called function inlining. So in many languages this is usually how a function call looks. We have some code that we're already executing, we then jump off into some other section of code which is our function, and then we return from that function later. There are some performance penalties to doing things this way, however. For one, we have the extra instructions, the function call instruction and the return instruction, but there are also probably costs of the processor having to read these two different memory sections. And while you don't always want to do it, function inlining is a way to remove these costs. So the idea is essentially that we just make function calls free. We just make it seem like you wrote those instructions in place of the function call. So first off we can get rid of these call and return instructions, and then all we have to do is really copy this code snippet into where the function call would have been. And there we have it, our function's been inlined. And this is the kind of optimization a translator might choose to do, to make the machine coded outputs perform better. You can't always trust translators to make the important optimizations for you though. Not only are there a lot of optimizations that translators can't usually do, but sometimes the translator can make the wrong decision. So maybe you can get a performance win by inlining it yourself, or telling the compiler please do inline this. An even more common optimization that translators often make is what I call constant baking. So say we have this high level code on the left, which aims to essentially print the value 15, but is doing so with some indirection. The compiler might generate this assembly code on the right, which corresponds very closely to exactly what was written in the high level code. Because 5 and 10 are actually constant values though, there's really no reason we should be doing this addition every time we run the program. It should be pre-computed into the code that the translator outputs, and so the translator could instead output this code, which saves an instruction by making the translator do the addition instead of the output program. Note by the way, before we move on, that translators often have a number of different optimization settings. Be careful before blindly switching all of these on though. Sometimes the compiler can make optimizations that break your code. Maybe your code is assuming something that the compiler does not assume. You do have to be careful with optimizing compilers. If you want to know more about this, do a bit of research on floating point optimizations, or the strict aliasing rule. Algorithms and asymptotic complexity are also very important to code performance as well. These details should be addressed before attempting most of the optimization advice in this course. It's usually relatively easy to focus on the logic of algorithms when programming in higher level languages. We're not really going to discuss algorithms much in this course though. I will quickly outline my point though about why algorithms are important. Say we have this array of numbers, and we're looking to search through this list for the number 22. Well, how should our code go about this? One way is to use a basic linear search. So we go through each item and we check if it's 22. So first we check 5, nope that's not 22, so then we check 8, then we check 10, and so on. Finally we get to 22 after quite a few comparisons, and we're done. What if we tried a different strategy to searching through this list though? A different algorithm? So instead of doing a linear search, let's try a binary search. So instead of searching through one by one from the start like we did with our linear search, let's make use of the fact that this data is ordered. So let's start by trying the item in the middle. Okay, 15. 15 is less than 22, so we now know this first half of the data is useless to us. So we can repeat the process on this upper half of the list. So in this case we discard the first half of the list and we want to try the value 19. Okay, it turns out 19 is less than 22 as well, so we do the same thing. And now we're done, we're finished, we found 22. And you may have noticed that our second approach here was theoretically faster. We did less comparisons to find the same value. And on a really big sorted list, this would make a huge difference. So I hope that demonstrates why algorithms are also extremely important. So now let's talk about the different types of translation. I think I slipped earlier in this video and used the word compiler instead of translator, but they're not synonyms. A compiler is a very particular type of translator. Essentially, the idea of a compiler is it's a program that takes your source code, your high-level language code, and it translates that or compiles that into some binary instructions, usually in the form of an executable file. You can then go ahead and execute these instructions as many times as you want, and you've only had to compile your source code into the machine instructions a single time. This is actually an extremely good model of translation, and is one that a lot of languages primarily use, including C. The kind of opposite to this, if you will, is interpretation. Instead of compiling your source code once into machine code, this is a program that reads your source code and executes it immediately while it's reading it. This means that you need your source code every time you want to run the program, because the interpreter has to reinterpret your source code every time. Clearly this is worse for performance, as you have this overhead of having to reinterpret the source code each time. This can be good for debugging purposes though. If something goes wrong while running your program, the interpreter can give you a lot of information about this, that perhaps a traditional compiler wouldn't be able to. Compilation advocates though will probably tell you that actually we can have this kind of debugging advantage with compilers. It's a little more difficult to build in, but it's entirely possible. Interpreters typically perform less complex automatic optimization on your code as well, because they don't have this advantage that compilers have, where you might not care how long a compiler takes to output an extremely optimized version of your program. We then have other forms of translation, which are kind of a mix of compilation and interpretation. So remember, compilation is source code straight to machine code, and then we can execute that machine code repeatedly, and interpretation is source code straight to execution. So the first mix of these two we're going to discuss is interpreted bytecode. The idea here is that your code is first compiled and then interpreted. So you compile to some middle ground code, so not machine code. So here we're saying we compile to some form of bytecode, and then that bytecode gets interpreted by an interpreter. This gives some of the advantages and some of the disadvantages of both compilation and interpretation. Personally, I'm not a fan of this method. Famously, Java traditionally used something like this. Really, a lot of the success of a system like this comes in the bytecode design. How do you want to design your bytecode to get the benefits of compilation and interpretation? Generally though, I've seen this method be the worst of both worlds. By having the bytecode, you lose a lot of the debugging advantages, you also lose some of the speed advantages of compilation. This can kind of work for cross-platform stuff though, so you can have a single compiler from your language to the bytecode, and then you can just have different platforms write their own interpreters, which is what Java basically did. Now the fourth method we're going to look at here is JIT Compilation. This stands for just-in-time compilation, and this mixes compilation and interpretation in a way that I think is actually very cool. Basically the idea is that it's kind of an interpreter, because it sort of executes the code as it's reading it, but it's sort of a compiler because what it's actually doing is reading the code and compiling it. The title actually explains it very well. Essentially it's compiling the code just in time to run it. And this can really be very useful. And by the way, sometimes this is sort of thrown on top of the whole bytecode idea. So sometimes you'll see JIT compiled bytecode. But anyway, one of the key advantages of doing something like this is in dynamic optimization. So as your program is running, the JIT compiler can say, hey, this section of code is executing an awful lot. And it might notice that actually in this current use case, this branch is taken along, these things seem to happen. And so it can say, well actually what I'm going to do is I'm going to recompile the code in a way that makes those things fast. So it can do optimization depending on how the program is actually executing, which is something that's quite difficult to do in traditional compilation. At the time of recording, JIT systems still tend to be slower than compiled ones, but JIT is a good idea. And actually with the right mix of pure compilation, so for example to a bytecode, and JIT compilation of that bytecode, you can get a lot of the advantages from all the methods we've described. So which is the best translation mechanism? Well, personally I'm not a fan of interpreted bytecode, but they all have their place. And in high performance situations, you're really talking about compilation or JIT compilation, both of which can be blazing fast. So this sort of leads into the question, which programming language should I use? And really this is another one where I want to answer it depends. There are an awful lot of factors that influence the answer to this question. Often languages themselves aren't tied to a particular translation model, although you don't see many C interpreters around. So to an extent you can say that, well, the language doesn't really matter. I can write in any language I'm familiar with, and then it really depends on the translator. And well, yes, that's true to an extent, but different languages make it easy to do different things. And some languages can express more details about how the translator should write the output code than others. C, for example, is an extremely powerful language, as it lets you directly manipulate memory, and this can allow for the generation of very efficient code. Whereas to get the same code out of other languages that don't let you do this, the translator would really have to work some magic. Plus, some languages make it easy to write secure code, some languages make it easy to write efficient code, some languages may have a more appealing syntax than others, maybe this makes searchability of the code easier, maybe it makes the code easier to refactor, maybe it makes the code more maintainable. Some languages make concurrency very easy. Some languages heavily push particular paradigms. For example, the Java language very much locks you into object-oriented design. It's actually very difficult to do something that isn't object-oriented in Java. Another thing that's definitely worth thinking about, along with the properties of the language itself and the translation mechanism, is the memory management mechanisms employed. C, for example, is a language where you manually manage memory. So if you want to get some extra memory that you haven't already been allocated, then you allocate that memory yourself and then you free that allocated memory yourself, for example using the malloc and free standard library functions in C. But in Java, things are different. You can allocate things all over the place and they'll just get freed for you, because Java is a garbage collected language, or GC'd for short. Manual versus automatic memory management is a huge discussion which we're not going to get into right now. If you're interested, please do some research on it. It's a very interesting discussion. But all I'm going to say is at some point you're probably going to have to think about memory. At the time of recording, memory is extremely important for performance. And so in my opinion, for high performance applications, you're going to almost always want to use manual memory management because it gives you that extra control that you need to squeeze the performance out of the code. And when you come down to optimizing your code, you're not fighting some black box garbage collector. You have control over the memory, you can decide what to do with it. Whereas if you're building a high performance application in something like Java, the lack of control with memory is probably going to bite you. If it's not a performance critical task, and you're already fast enough, then who cares, use whatever you want. Garbage collection though, this kind of automatic memory management, definitely has its downsides. And personally, I'm all for manual memory management, even in non-performance critical contexts, because I think the extra control is really good, and I don't think it's as difficult to manage memory most of the time as people make it out to be. But anyway, I said we weren't going to get into that discussion. Pretty much, choosing a programming language is difficult. There are a lot of different factors, and ultimately you should try and choose the right tool for the job. So that is the end of this video, and I will see you next time.